So at this point, it's my pleasure to introduce today's colloquium speaker, Dr. Nathalie Cabrol. Nathalie received her PhD in planetary sciences from Sorbonne University in Paris some years ago with her husband Edmond Grin, who is here and is also co-editor of the book that Nathalie is going to speak about today. Nathalie and Edmond were the team that argued strongly for the Gusev crater landing site for the rover Spirit, and their arguments won in that competition, and it's something that I brag about every time I speak of you. So in that sense, and everything related to that, Nathalie is a planetary scientist looking at Mars, but she is also quite an explorer here on Earth. She has spent a good deal of time in the high altitude lakes in the Andes, studying life there that exists in extremely cold, dry, and high UV environments, and trying to understand what that might tell us about the potential life that might exist in places like Mars. And so she is an explorer in planetary science of high caliber, has been a principal investigator here at the SETI Institute for roughly a dozen years. Our website was actually down when I went to go back and look at what your start date was, so it's roughly a dozen years, right?
September 97?
97, okay, 13 years then. Okay, so I'm off by one. Nathalie will be speaking to us today on a new book that she and Edmond served as editors. The book is entitled Lakes on Mars, Their Past, Present, and Future Explorations. And Nathalie, welcome. We look forward to your time.
Well, thank you very much.
The lights?
Yes, please. That would help.
They're the ones. The ones by the door.
The one that shut down the entire building.
And it turned out about half the building. As I said, this room wasn't built for this job. There we go.
Now we're in the dark. Okay, well, you know, it's been a while since I've talked about lakes on Mars, and some people might have misled this, thinking that I was not interested anymore in the subject. That's very far from the reality. On the contrary, sometimes in life you have to take a little distance to get closer. That's planetary scientist logic. But that's exactly what happened when we decided to go in the Andes. In fact, we took a little and to understand what was going on Mars. But it was always about Mars, and lakes on Mars are and one of my highest priorities as far as research goes. So this is why little Marvin here said, here she goes again. Well, yeah, but you know, things have changed since the last time I talked about lakes on Mars. And when you look at the data today, it's absolutely spectacular. We are very far from the low, well, relatively low resolution of the Viking images. Here you have now details that are down to the meter. You are seeing layers and layers, and some of those here are putative lake sediment. They might be mixed with other things, but at least some of them maybe. And what you see here is the meander of a river. So a number of things have changed. It's not field work yet, but we're getting close of having as much detail as that from orbit. The other thing that has changed too is that we need to take this data overload, which is coming from morphology, from topography, from mineralogy, and try to make sense of it, and make sense of it at a very different scale. And what I noted is that this step is only slowly taking place. And we still tend to see Mars at low resolution in the process. And we are trying to take all these details and put them in this frame of mind. We need to, I will talk more about that. But today I'm going to talk to you about why lakes are so important, and important enough that we decided it was time to write a book about it. If you had many books about water on Mars. Interestingly enough, not too many people a while ago cared about how this water would end up and where it would end up into. So why are they important? They are sentinels of climate change. This is one of my good colleagues, Fred Williamson, wrote that in Science a year ago. And the reason why going there is telling us about climate is because the lakes are small features at geological scale. And they react very rapidly to whatever happens in their watershed. And so it's going to be recorded in their sediments. If precipitation change, there will be more sediments. If there is more water, less sediment, the chemistry will change. So they're a telltale of what's going on as far as climate goes. And also, I didn't write that, but they are fraddles of life because they create an anoxic environment when you have dead organisms and they fall at the bottom of those lakes. They are trapped, and this is a good place to look for fossils. So today, I am going to review a little bit of that. What is the Martian record today telling us about water activity and climate conditions at the time of their formation on Mars? And I will talk also about the evidence for very large lakes on Mars. Why I'm focusing on that, because those are also very important for what they tell us about climate, but also they were large enough so that some of them could have altered climate on their own. And then I will, if I can get to that, tell you a little bit about the role of lakes and ponds in the present and future exploration of Mars. So, more words. There will be nice pictures, I promise, but I want to make an important point here. Does their presence support the model of early sustained water activity? If you look at the record of lakes on Mars, and that dates back from Viking and Scott et al. Started to look at them closely. We did some of that work with Edmond as well. Well, we couldn't see many. And that might be a bias from resolution, just because Viking resolution was bad. It was 200 meter resolution per pixel on average. And the topography was even worse. We didn't have any detail. It was plus or minus 1 kilometer in elevation. So try to do some hydrology work with that. The only way we could be sure that we had depressions on Mars, except for the very big thing, was to look at impact crater. We know that valley networks would converge in those craters, and if water went in those valleys, then we would have lakes in those craters. So Edmond and I took care of that. We found 149 of those lakes. And the most recent global survey is that of Bassett and Head, and they look at not the entire population of lakes. They look for specific lakes I'll show in a moment. And they found 210. So how does this compare to what we see on Earth here? And it's a completely unfair comparison, all right? But I just want to make a point. We have 304 million lakes, ponds, and impoundments on Earth. And 18,200 something are superior to 1 square kilometer. And I'm going to look at this number because this is the kind of size that we can now get access to on Mars. So what we need to understand is whether this number is original. And don't misunderstand me, I'm not saying that there were 210 lakes formed on Mars in the past. There has been erosion, we know that, but is this a little erosion? Or is this a good deal of erosion, so that we are not seeing 99% of the lakes, okay? We need to understand that just because the conclusion for habitability are drastically different. Now, we cannot look at lake without looking at the entire assemblage of features, landforms, and other things that make them what they are. And we go back to the source and we look at what the hydrographic system says about that. Back at Viking, because the resolution was so poor, we would see very, very little rivers and channels. And then the conclusion at the time was that the hydrographic system on Mars was immature. So the reason being that maybe there was not that much precipitation on Mars. Today, you look at the same region exactly, and this is what you see. So this is getting a lot better, right? Our perception of Mars is that there was a lot more water, or at least, we have a good sense now that water formed those things. But I believe, correct me if I'm wrong, Jeff, but there is something like 40,000 streams on Mars that have been cataloged so far.
Yeah, that's about right.
And so that sounds like a lot. Well, imagine that in the US alone, you have 250,000 streams. So we have to put things into perspective, okay? So, yes, water, a lot more water than we thought, but is this a lot of water? And then when you look at the age of those channels and valleys, you see that they are associated mainly with old terrains, right? And that goes with the idea that Mars was a more favorable place for surface liquid water early on, and later on, you still find some recent Amazonian, and Amazonian starts 3 billion years ago, in the Tarsus region, and some Hesperian flow in the Hesperian Basin. But basically, valleys and channels are old. And this is pretty much in the same area that you find the lakes on Mars. Once again, this is not the entire record at high resolution. It hasn't been done yet. And Edmond and I are going to work on this as soon as we can. But right now, let's just focus on the work of Fassett and Al. What you see here is the distribution of open lake system. What an open lake system is, it's basically a flow-through system whereby a river goes down, enters a basin, and flows long enough that it will erode the other side of the basin and continue flowing, and you can form a chain of lake like that. So this is what we call open system basins. And why Fassett and Head chose that, it's because to them, they were the evidence that there was sustained flow on Mars, right? So, 210, what was their main conclusion about that? Their main conclusions are extremely important at many levels. They say that the largest lakes on early Mars were comparable to the small seas on modern Earth. You need a lot of water to do that. We're talking about hundreds of thousands of square kilometer basins. We're not talking about small things. This is not the 1 kilometer square basin I was talking to you about. The second thing is that they are saying that there is evidence for a widespread resurfacing of the floor of these basins. And this is really important because that may help us lean more towards the heavily resurfaced Mars, meaning that maybe we're not seeing all the record of Martian lakes. And their next conclusion is that, well, you have lots of valley networks and channel converging to basins in the uplands, and towards the north of Mars, you had more of groundwater-related type of systems. So, this is well and good, but still, they are rare. And we need to look at other evidence to understand how they fit. So the next best evidence we can look at is deltas. And what is a delta? A delta is a sedimentary deposit that forms when a river enters a body of water. So there are good evidence that there was water somewhere, and we know their morphology and what they mean. And when Gaetano and Brian started to work on deltas on Mars, they had that in mind, looking for the activity of water on Mars, and also they were looking for something else, and they might have found it. Here what you see, the red squares, are deltas that are located on this S1, S2 line. And what is the S1, S2 line? Is the shoreline level 1 and shoreline level 2 of the putative northern Martian Ocean. So there are some of those delta that seems to be at the right elevation. This is the elevation here, this is the longitude. They seem to be on the same elevation, meaning that it entered a body of water, possibly that was located, that had an equipotential line located at that elevation between minus 2 and 3 kilometer elevation. What you see here, the gray dots, are also another putative shoreline. This is the Arabia shoreline. So that's interesting. It seems that the number of delta is low as well. On the other hand, the location is consistent with the presence of an ancient ocean on Mars. So if we do have an ocean on Mars early in the history of the planet, believe me, we don't have any problem at all anymore, just because everybody who has been modeling, and Jeff has been part of these people here, tells you that if you put a body of water of that size in the northern hemisphere, then you have a milder atmosphere, you have precipitation, and then you can start this hydrological cycle. Is this the proof? No, but this is consistent with that. Now, what does the morphology of this delta is telling us? The morphology of the delta is consistent with, like this one here, with sustained flow, flow that lasted for a long time. On the other hand, you have those deltas here that probably formed out of a single outburst, and that can last a few tens of years, but very short duration flow. And on the other hand, again, you have this kind of morphology that tells you that maybe this deposit was formed under ice. So what does that mean? It's very confusing when you look at the evidence, flatly on a horizontal layer like that. It tells you it could be cold, could have been mild, it could have been what? We don't know. It could have been sustained, it could have been short. Now, another argument I want to talk about for a second is that I've heard often people saying, well, you know what, there are very few lakes on Mars, and there are even less deltas on Earth. Well, do you know how many deltas we do have in our hyperactive hydrological planet? 51. 51 major deltas on Earth. Actually, no, I'm wrong. It's 31. It's 31. So, actually, Mars is showing more deltas than Earth today. So, just a point to carry home. We need to look beyond the numbers sometimes. So, what does that tell? We might never know for the deltas, but we might have a way to go back in time as far as lakes are concerned. This is what I call forensic limnology. Limnology is the science of lakes, and here planet Earth is coming to the rescue, and this is very recent work. It seems so that the lakes on Earth are governed by a parallel function, which means that they have a distribution in size and their frequency that respond to the power law. And what is interesting is that no matter where you are, I didn't have room to put the regions here, but this represents the entire Earth. This is a global survey. No matter what the climate, no matter what is the origin of water, they all have the same slope of power law. And which, when you think about it, say, why is that? Well, then you need to go back a little bit in time and relate to the work by Mandelbrot. And this is the fractal nature of the landscapes. Very simply, nature is producing a lot more small things than large things. And they can be arranged and they can be described by power law function. And that's the case for depressions. What is a lake? A lake is water ponding in a depression, okay? And so, what happens if you open the faucet for 5 minutes, randomly? Well, water by gravity is going to pond into the first law that it finds. So, if you do that randomly for 5 minutes, there's not going to be any organization of your distribution of lake. It can be 2 big lakes, it can be 2 small lakes, it can be anything. To get to such organization, you need to have sustained water activity for a long time and widespread so that the lake science frequency distribution can conform to that of depressions. And I started having light bulbs lighting on top of my head, and I talked to Edmond about that, and I say, what if we were looking to the lakes on Mars in a very different way? Usually we look at their spatial distribution. Now, what if? The only thing we had recent was the work by Facet et al. It's not, as I said, complete, but it's a subsample, and it is very representative, especially it is representative of sustained weather activity. So we started to look at that, and we plotted those lakes according to size and according to distribution, and this is what happened. So, what to do that? You can see some family resemblance between the slope of parallel between those regions here. Look at that. As you are expecting, this here, this part of the curve, you have a strong deviation to the slope, and it's a negative deviation because, as we said earlier, small things tend to erode a lot faster than big things, right? So you see all these basins starting 100 kilometers started to curve that way. You see the same thing in that region here. These are latitudes, different regions of Mars. But what I found most interesting in that distribution as well is that you see those deviations to the slope of parallel. You see the same thing over and over, here, here, here. So maybe this distribution is also telling us something else. Those deviations to the slope, those negative deviations might signal times where this record has been eroded, but it hasn't been eroded in one place. It has been eroded at scale that go beyond region, that might be at planet scale. It's a very beginning of the whole story. We need to go to the entire record and check all that record and actually plot those. But it's very encouraging. And I'm making a statement today here that if we confirm that the Martian lakes are, their size frequency distribution is following this slope of parallel, then we might have part of our answer here. It means that water was sustained long enough and widespread enough that they could conform to the depression that are located on Mars. Interestingly enough, and also acknowledging that it's only a partial record, you see the slope here is about 60% that of planet Earth. I have a few ideas about what it might be about, but I won't talk about it yet. But it might just be the size of a planet and the number of depression of different sizes compared to the Earth. It's about, Mars is about 60% the size of Earth, right? Or something along those lines. I don't know if this slope is really representative yet, but once again, this is preliminary thought and work. We need to do a lot more than that. But this is, to me, this is consistent. And also, this is where Mother Nature is helping us too, is that how you're going to reconstruct the Martian record as far as is concerned, because they're eroded. Well, large lakes and large basins will be less eroded than small ones. So we might have a population of large lakes that is closer to their original number than the population of smaller lakes. And so maybe we will never be able to get back to the original record, but we might be able to get a better idea of how many lakes there were on Mars. And also what I like about this approach is that it really doesn't need to look at existing climate model, doesn't care if it was wet or cold or what people are saying. It doesn't care about mineralogy. It's just here. It's just number and size, and then you look at them, you know it works on Earth. If you see the same thing on Mars, then that sends you a message. Okay, so climate, we're talking about it. Things have changed too for that. In the past year, we have seen carbonates raining on Mars, well, so to speak. But it's still not in the amount we would like to see. We found carbonates on Mars, that's a very big deal. We found a lot of aqueous minerals, we found clays, we found hydrated sulfates. But in the end, when you look at that record, is this telling us about Mars was wetter or warmer or colder or the whole spectrum of models that we've seen in the past years? What it tells you is that a variety of physical conditions can account for this record. And David Catlin goes as far as saying that you don't need to have a warm atmosphere on early Mars to explain the formation of clays on Mars. Carbonates, they're a very big deal. We've been looking for them for 30 or 40 years, and we have them now. Do we have our proof? No, I don't think so. What I would like to see is the record of the Cathy Sea, those big carbonate formations all over the place, and we're finding small spots of them. Does that mean that they didn't exist, this large formation? I don't think that says they didn't exist, but we don't see them. They might be buried, or they might be recycled because we had an acidic environment in the Hesperian. That might just be the key here. Or they might just have formed very episodically and related to very specific regional condition. Interestingly enough, those carbonates are found very close to volcanic centers. And another hypothesis is that they were just formed out of volcanic activity. Another interesting thing when you're looking at the succession of climate in the models we have today, usually we tend to think about, well, Mars warmer, getting cooler and drier. So it would make sense to have carbonate, sulfate, etc. Well, what we see is that Gustav's carbonate are the oldest. So that's fine. And then we have sulfates in Meridiani. But those sulfates in Meridiani are actually older than the carbonates we find in Nili fossé. So what does that mean? Does that mean that climate was so chaotic that conditions change? I think it might be part of the answer. Mars has astronomical parameters that are so different than the Earth that maybe the climate change there are anything that we can even grasp. So it might explain some of the ambiguous record. I also do think that we haven't enough thought about the importance of the regional factors. And this is where I'm heading at with that, is just that Mars has a season-dependent climate, exactly like Earth. So you are expecting a diversity of environment and morphology and mineralogy at any time. Okay? It doesn't have to be monotonical. Okay? You see how the conditions are different in California and in Washington. Okay? And you're forming different minerals and you have different temperatures, etc. Now we have the resolution to get into that level of detail. Some studies have started to do that. I don't think that there is enough emphasis on that yet, but please do not neglect the role of elevation and relief and all the other factors that can explain what you see. Basically, what I'm saying is that look at the regional factors exactly like we do on Earth. Okay. Warmer and wet, or cold and weather. This is my version, or cold or weather or whatever. We've heard about everything. I don't care. I really don't. It doesn't matter as long as water can circulate and pond on Mars, and it can. Obviously, we see it, right? Just like remind me of this bug. I don't know the translation in English, the name of that bug. But there is this story that according to the laws of physics and mathematics, these bugs couldn't fly. Well, he doesn't know the math and the physics, and he still flies. Okay? So we see lakes, we see streams. They were actually formed, and the liquid is pretty certainly now. We're almost convinced it's water, and so we need to make our model fit, and Mars is not going to fit our model. So all the models existing today work for forming lakes on Mars, whether it's a cooler planet or a warmer planet. And if literally life had cold feet on Mars and needed some warmth, then we don't have any problems because we already found warm ponds, like in Gusev or in Nili-Fossé. We have plenty of evidence of hydrothermal activity. So there is plenty of nice spot for life to take a bath if they really wanted it. Mike Carr and Jim Head, who wrote a fantastic chapter, a review on our book, are stating that maybe Mars was never warmer than the Arctic region here on Earth today. And that would make sense. Mars is farther away, always has been farther away from the sun than the Earth. And by the way, the young sun was fainter than the present sun. So to me, it doesn't matter, as long as water can circulate, and we know it could. So nice pictures now. I'm going to talk about the large Martian lake. As I was saying at the beginning, I focus on those because they send a message about the climate and the water activity at the time of their formation. And they do also have the potential to alter the climate on their own, at least regionally. And also they were stable environment for life. Lakes can be stable. They are interesting beasts. I'll talk more about that too. But they provide a very nice environment for life. And what I'm going to talk about today, I'm going to present to you the evidence that the co-author in these books have been presenting. And knowing that all of these large Martian lakes are still very controversial. There is the same thing that has been going on since Viking, the volcanic hypothesis versus the lake hypothesis. I'm going to start with Manhattan Valleys. This one is not in the book. It's a work that dates back 2002 and 2003 by Irvine and al. But it's a very important for a point I want to make. And then we'll see a lake in Valles Marineris and Valles and Elysium. Okay, Manhattan Valleys. Why am I interested in Manhattan Valleys? I wrote my master thesis on Manhattan Valleys, so that was by 1986. But other people have been working on it with, more higher resolution. Why is it so important? A couple of things. What you see here is the work by Irvine et al. And they found with monotopography and at the time the Mars Global Surveyor data that there was a huge basin. Here you have Manhattan Valley. Manhattan Valley is an outflow that's about 900 kilometers long. So you can see that this basin is already 2,500 kilometers long here. And so we had issues in explaining how this lake was this valley was formed. What were the different episodes of formation, and Irvine et al. Presented a very interesting model of that. So what they see here is this huge basin, and these basins are sort of interlocked with each other. Not all of them communicate with each other. The one that really interests directly Manhattan Valleys are this one here and all this one here. So the idea is that at some point early on in the history of Mars, in the Noachian, which is the most ancient geological period, this lake that was fed by precipitation and groundwater, let me go back for a moment, this entire area would have filled with water. And what is so important, because it places a lake the size almost of the Caspian Sea in the highland of Mars in the mid-latitude. That's a very big deal climatically. So what happened then? Well, this lake started to overspill. And so there was erosion here in a spillway, and then the whole water went down following that topography, down here, pounding in Gusev, eroding that rim, and ended up in the northern Celtic terrain, right at the foot of Apollinaris Patera, which is a very large volcano. They provided some evidence of a shorelines and water high stand in the upland. You see this valley here, they all terminate very abruptly, which is generally a sign that there was a body of something. We would hope that's a body of water. So the valley just stopped all at the same level right here. The other point, I'm sure I'm going to make Jeff laugh here because probably the one who knows where I'm coming from with that. But the point that I want to make is that, and that Irvine shows here, is that, well, the sediment of Manhattan Valleys from that event here were then buried by subsequent geological events, including lava flows, and including the lava flows that we see in Gusev right here. But now when you think, it means that early on there was water activity and pondings in this area. So the hydrovolcanic in Gusev and at home plate. The reason I'm talking about this here, if you remember, Gusev is at the receiving end of Madian Valleys right here. And we have evidence with the rover Spirit of a region where we had hydrovolcanisms, which means that magma, explosive volcanism, which means that magma at some point encountered water underground and everything exploded. You find the telltales of that. You find the lapides. This is consistent with that. You find the silica deposit, which are consistent with a hydrothermal pool. And this is the home plate area where all this evidence has been found. My question then is, how do you put water in this area of Gusev if you didn't have a river flowing through it and a lake in the first place in Gusev? You might have had groundwater regionally because Gusev is such a huge basin. But we have a very nice surface flow event that could also explain all of that. And I'd like to think that Ma'adim and its activity are somehow responsible for the activity we see at the home plate. So where Jeff is going to laugh is the following. Does she really think that there was a lake in Gusev 6 years later? Yes, sir. Can I prove it? No. Valles Marineris now. This too is very important. Here, before with Madian Valleys, we saw a very large lake. This one hasn't been contested too much, actually. All of them have been contested, but this one wasn't. So a large lake in Madian Valleys. And now we're talking about Valles Marineris. This here too is a big deal because Valles Marineris is the largest canyon in the solar system. And people who have been working on this area of Mars are suggesting 3 different types of lakes in that area. There is the what I call the megascale. Barbara Lukita didn't call it the megascale lake, but I did because this lake would occupy the entire Valles Marineris, if you can imagine that. And the evidence is from interior layer deposit, and this one is still very controversial. There is what I call the mesoscale lake, which is about half of Valles Marineris to the east, and it has morphological and topographical support. And I haven't seen too many controversy about this one. And then everybody agrees that just because of the configuration of Valles Marineris, we had to have small lakes in Valles Marineris. And we have also the mineralogical evidence for that too. So what about the sources of water? All the models are showing that groundwater was dominant. And I'll talk about the sources, the potential sources later. There is a minor contribution for by surface networks. And an interesting hypothesis is the role of the putative Northern Ocean. Some people think that the benches we're talking about in Valles Marineris are pretty much located, some of them, at the level where the shoreline I showed you earlier is located for the Northern Ocean. The issue with that hypothesis is that there is no inflow feature from the plain into Valles Marineris. We only have outflow features coming from Valles Marineris to the northern plain. I think we can go around the argument that the inflow feature were eroded, but that's speculation. Okay, so the mega lake. This is Barbell's favorite hypothesis. What you see here is a mapping of the interior layer deposit. And what you see down below here is places on Mars where the mineralogy has been found consistent with the alteration by water. The issues with the interior layer deposit is that some people are saying that they're exhumed and they're older than the Barbell says they are. Some say that they are plastered on the canyon's wall. And there is also an issue about their origin. Are they volcanic? Are they alien? Are they lacustrine? Or are they part of a sub-ice volcanic activity? Are they all the above? There is still a lot of discussion going on here. But they certainly do some very nice landscape out there in Valles Marineris. You see the high-rise image. You see the scale here. This is what we have to learn to work with. And all of these represent layers and layers and layers. And in those layers, you find opal and other hydrated silica and minerals that really show that there was water out there. So I don't know if there was a large lake in Valles Marineris. Barbel does a very nice job in this book. She makes a 50-page review about the whole thing, and she, like the other authors, really looked critically at this question and look at all the other hypotheses. And then she says why she prefers the lake hypothesis. But if that was the case, there was a gigantic lake in Valles Marineris earlier. The other one, the mesoscale lake. This one is episodic ponding caused by groundwater activity and Celtic terrain outburst of water in Valles Marineris. And that's the work of Harrison and Chapman, and they too make a very nice description in the book. The little red dots that you see here are the benches that they argue are evidence for an equipotential level in Valles Marineris, and they argue that this was related to lacustrine activity. So topography is consistent, the bench morphology is really convincing, and if this was the case, then we had 100,000 cubic kilometer lake with a depth of a little over 800 meters. That was not a small swimming pool. That was something very serious. That was probably stable long enough, because you need sometimes to get rid of that. Unfortunately, apparently there is an outflow to the west, which means that this lake might have, at least one of them might have found some rapid end. So here is the topography work that Harrison and Chapman have done. You see the benches, this is the elevation. All these benches made at the same elevation everywhere. My word of caution about the benches is that Valles Marineris is probably the tectonic feature of the solar system. And so benches can be formed by tectonic activity too. But when you really look at the morphology of these benches, they are really sinuous. You see them here. You find them everywhere here. If it was more tectonic in nature, you would expect that they may be more cutting through the landscape rather than actually wrapping around the landscape. As far as topography goes, the elevation here of the valley tells you also that there is a nice spillway in this region that is supported by scour channels and morphology that is unique to this region in Valles Marineris. So Keith Harrison made a model of how this lake would have the spillway route for this lake would have gone into the northern plain. So the benches suggest that this lake changed levels episodically, but it remained at these levels long enough so that you can form terraces that don't form overnight, okay? And that is consistent with the model that many researchers have been working on. I'm referencing to Mary Chapman here and Ginny Gulick and co-worker here. But people like Baker, Jim Dunn, Bob Anderson, and many others have worked on a system where Tharsis, this huge volcanic center, would act as an engine to circulate the water and provide groundwater in the area. And Valles Marineris is definitely the sink, the topographic glow that's right there. So it makes a lot of sense. But it's good to have the mineralogy, the morphology, and the topography that says that that could be the case. And what is interesting, in their work too, is that it might be, if it existed, one of the most recent, youngest large lakes on Mars. There is younger than that. Now, Hellas. Hellas is definitely the big sink on Mars. This is the deepest depression on the planet. And when you look at the work by Sharon Wilson and Jeff Moore and co-workers here, you see that the whole area here, all the little blue things that you see, maybe not so well from where you are at, are valley networks and channel, and of course there are conversion towards the center of the basin. So you would expect that Hellas would be a sink for volatiles throughout Mars history, and you would also expect that if water ponded, it could stay a little longer than anywhere else just because of the pressure at the bottom of that hole. So I think that everybody agrees that there was some kind of lacustrine activity in Hellas at some point. But those guys are really getting to the next level by stating that a lake might have occupied most of Hellas. So that would have been some gigantic body of water here. Hellas is a 2,500 kilometer basin. So what is the evidence for that? The evidence is, well, there is the topography, once again. They are seeing terraces that dip inward, and also layers, not interior layer deposit, but layer deposit that are all located at the same elevation. That would be consistent maybe with a lake level or a series of lake levels here. My only word of caution here, and I am far from having read everything about the subject, so maybe I'm going to say something that is irrelevant, but I've looked into the channels in Hellas back in '91 for my PhD thesis, and I found interesting that the changes and the levels and the terraces that we found there were exactly spaced as you would expect them if they were the result of the basin structure. So I don't know how much this argument can enter that scenario, and I'm definitely not against the fact that those terraces can have been later on covered by lacustrine sediment. But I think it would be interesting to look how this topography that relates to the lake meshes into the structure of the basin. Now, Sharon and Jeff and the colleagues are not the only one. There are other groups that are working on Hellas, and they are seeing all sorts of morphologies as well. Here is another topographic map of Hellas. You see Dow Valles, Marquis Valles entering the floor of the basin here. And if you look closely, you can see this channel maybe continuing down there. And some people say that they have the same morphology as submarine channels on Earth. So this is another argument for a large body of water in Hellas at some point. The layer deposits are found, I showed you on the map, around that same elevation, and it's also found in the intercrater plane. And what they are saying too is that the slope of the terraces associated with the Punitive Lake would be going inward. Once again, this is not inconsistent with structure, but it might be consistent with the lake hypothesis too. And the mineralogical evidence is given by clays and iridated sulfates. And there too, you can explain clays many different ways, but that definitely includes lakes. I am completely sold to lacustrine activity. Hellas was the best place to get those. A lake occupying the whole basin would have been an incredible sight for sure. So here is another view. I couldn't help but add this high-rise image. There again, this is about 100 meters here. I don't know if those lakes, those sediments were deposited by lakes, but the way they are deposited in a very planar fashion, horizontally, And so that means that they were deposited in a low energy environment. And so that can be water, that can be also ashes deposited during volcanic eruption. That can be all the above. They might not exclude each other. Mars was a very active planet. There is other evidence. Those incredible, how do you call them, taffy pool?
Honeycomb.
Honeycomb, taffy pool, you choose your candy. Deposit here that have been explained. I have another one here that's even more remarkable, that are being explained as potentially soft sediment deformed under the pressure of ice. Others say they might be related to volcanic activity and distortions linked to convection in this region of Hellas. So, once again, this is a lake that, well, a series of lakes that would continue into the Hesperian. And so this mark really, if they were there and they were as large as those workers are saying, then it's another picture of Mars, just because you don't put that much water in the same place and not change the climate significantly. You would expect then to have snowfalls on the rim of Hellas, for instance, just associated with evaporation in this area. And that might be related to all these debris flows that we're seeing today. That makes sense. That makes a lot of sense. So now we are getting to the most recent of these periodic large lakes on Mars. And this one is really very controversial. People are not getting verbal or physical about this, but there is a lot of discussion about what's going on in Elysium. Everybody has seen in one journal or another this image here. And some people interpret this as a pack ice style, as you would see in the Arctic Ocean or even in a New York harbor during very cold winter. But others just say it's platy lava flow, and water doesn't have anything to do with it. And everybody agrees that it is young. It is less than 10 million years old. And so that throws completely out all of our notion of Mars getting really cold and dry, etc. It might have been localized. This is apparently what happened, and very temporary, but it was there, and it was there recently. And there has been a recent study, actually a few studies, but I'm going to focus on the evidence that has been recently presented and included in the book by Matt Ball and other. So here is the Elysium Basin. The first thing that you see when you look at the topographic map here is that it's a very flat place. You are between 2,500 elevation here, meter elevation. In fact, there is only 26 meters of difference around all this area, which is several thousand kilometers wide. So there too, there is good supportive evidence that we have a basin and potentially an equipotential level around that place. Now, the argument for water ponding there is Athabasca Valles. And this is an outflow sourcing somewhere in there. And what you see here, the black arrows, are the direction of flows as they were mapped by Bomeda, considering the material piling up against obstacles. And so you see that it reaches the center of this basin here, but you have other basins, and the idea is that the main basin spilled over and filled some of the smaller basin, and channels connect the lower basin, etc., etc. So it's a spill and fill kind of scenario. And there is morphology to support what we are saying. And this area is characterized by polygonal terrains. You don't see them too much here, but these polygonal terrains in some places here are completely eroded, and you see channels flowing out of that. It is in this area here. So the idea, at least for Matt and others, is that it shows the erosion of the polygonal terrain. And the polygonal terrain are polygonal because they are ice-rich. This is their argument, as you see in periglacial regions on Earth. And then you have the loss of liquid, erosion, and flow. And see the region here, the erosion, to them that is typical, those niches, of the loss of liquid water. If we continue, they're also observing what they call cataracts. And you see this outflow channel here. You have some sort of streamline islands, cataracts, and flow feature. And they said this resembles very much what we see in Washington in the Scadden Channel area. And then they also said that there is a suite, really, of morphology that is best explained by ice-rich subsurface. And you see stone circles and streamline islands and bars. And so for them, really, this is a nice suite of evidence that's consistent with the work of liquid water. So it would be a transient recent Paleo Lake, and would be linked to a sudden release of water. So it's not something that flowed for a long time or stayed for a long time, but it was there and it was big. I think that they have some interesting morphological evidence to support their case. And there are still a couple of scenarios out there to explain what we're seeing. People think that, yeah, Athabasca valleys definitely flowed there, but what the evidence we're seeing is the evidence left by a lava flow that followed the water flow. And Matt is going for the no lava and one or more fluvial flood. And they say that to explain the whole evidence, lava would have to act like water and enter like an ice-rich terrain. So this is where we are at with the large lakes. Once again, this is, and all the hypotheses, all the models are very much detailed in that book. What I want to reemphasize here is that all the authors have made a great effort in looking at all the possibilities. It's not like what Vic Baker calls in the forward an hydrophilic team looking, liking water and just saying there was water everywhere on Mars, etc., etc. No, they are looking at different hypotheses. Is this water? Is this lava? Is this alien, etc.? And in the end, they tell you why they still prefer the water hypothesis, just because the evidence is consistent with that. But if those big lakes were there, then we definitely have a very different planet in front of us compared to the one we thought we knew a few years ago. Now, are we exploring ponds and lakes today on Mars? Yes, we are, at least for the ponds part. The lake I was hoping to explore is a few hundred meters below the wells of Spirit. That doesn't matter because what we learned is so very important there. The Mars rover demonstrated past habitability on Mars, and Gusev and Meridiania, such extraordinary sites, so very different. And they are presenting us with two very different aquatic environments. One is warm, volcanic, and hydrothermal, and the other one, it looks pretty much, I think that John Rotzinger used that image here, show you some little ponds of water in between sand dunes. So, we also, as we saw, know that evidence is mounting that there were very big lakes on Mars. And those lakes are an essential part of Mars habitability. We know that they are localized on Earth. And I think they must remain top priorities for future exploration as we're seeking science of life. Why is that? Well, they are protected habitats in a planet that was changing so rapidly and so drastically. You can expect that the water column would serve as a buffer against some of the effect of this changing climate. You have a thinning atmosphere, which means that you're going to have increased UV, and then the cooling and the thinning is going of this atmosphere is going to make temperature change very rapidly. I'm not talking about a change, in a few hundred years' time. I'm talking about the 10 or 20 degrees C that the temperature is going to change in a fraction of a few seconds. We see that at high altitude. In the end, is in a thin atmosphere that's probably very close to what we have on Mars. You can have drastic changes of temperature. The thermometers goes like that. So once you're in the water, you are somehow protected against all of that. But then it's a give and take situation. It's not all good and beautiful. In the first place, your water is going to go anyway. It's evaporating, so you're doomed. If you are not evolving, you're doomed. But it might not be monotonical. It might not be going from bad to worse to doom. What happens when you look at analog places, such as the lake we are exploring in the Andes, you see that, in fact, extremes combine. For instance, yes, when precipitation stops, you have lots of evaporation, but when you have lots of evaporation, you have more salts that are being precipitated in the water. So you have more dissolved solid in the water. And in turn, that scatters the UV a lot higher in the water column. We've seen that. So the water column is getting smaller, but UV is being stopped higher. So that works well. And then when it's getting cold, you have ice on top of your head. The lake is going to ice in. And ice is nice because it's going to temperate the temperature of the water underneath. But then the giveaway part is that then you're also cutting part of the good radiation that you would like to receive, the photosynthetic part. You don't have enough or necessarily what you need to do photosynthesis. So this is the give and take thing. And ultimately, as I said, this water is going to go. So what you need to do is to have enough time to go from a lot of water to not so much water to no water anymore. And then you need to have species that were able to transition from a water aquatic environment to a subsurface environment. I think that is really the issue here. And pretty much the question is whether they had enough time to do that. So just real quickly, if that thing is not frozen. Okay. This is, there is no name on this cladogram just because it's not important here, but this is a cladogram. This is done out of the DNA of some of the bacteria studies that have been made for the high lakes. And what you see here is that what happens is that you have a loss of biodiversity. You will have species that are going to die right away, others that will die along, and then you will have the ones that are going to be very successful and adapt very quickly. So you can expect that on Mars because that planet was changing so fast. I think this is the picture we have to have in mind, at least as until those species find a stable niches, possibly underground. So they have several characteristics. Ecosystem might have been not very diverse, but with very resilient microorganism. And the thought that I had is that maybe life on Mars, if any, might still have been diverse just because you had so many isolated niches that a microorganism needed to adapt to those specific niches. Okay? So life might have been seeded everywhere on Mars through the same ways that we have on Earth here, which is water, which is air, which is but then they had to really adapt to their specific niches. So this is where maybe biodiversity is going to come about. Already, what about lakes or putative lakes for the future exploration of Mars? Well, let's say that I think that the program has got the point across that lakes are important. When the site selection started a few years ago for the Mars Science Lab mission, among the sites that were presented, there were 12 candidate lake sites at the very first workshop. And we're somewhat happy to see with Edmond that 5 of those were still backups of Gusev in 2001 for the Spirit rover in the MER mission. And today, as of today, they are making 3 out of the 4 final candidate that will be decided in a few months now for MSL. So no matter what is going to be selected, no matter what site is going to be selected, just expect it to be spectacular. Here it's Holden crater with the Ostboy Valles entering into Holden, and see all this layering here. The people who have been working on this area, John Grant and Rod Irvin, etc., who wrote a paper in our book, see traces of fluvial and lacustrine activity in there. There is Gale crater. Gale was the backup for Gusev in 2001. And there you see a little channel in the middle of all these layers here. They're most likely, not all of them are lake sediment. They're most likely from volcanic activity and from Aeolian activity. But here, there might be a chance just because there is this little channel bed that there are some aqueous sediment. And there is Mars Valleys. This is the only valley among all of these pulative lakes. And this is a very interesting place just because you have lots of clays and they are very ancient. So here we have a window in time into the Martian past. And there is the delta of Everswald, which is also a pulative impact crater lake. So I'm going to stop here. But I wanted to thank again the cast of character who helped us with Edmond to pull together this incredible book. And these are all the people who contributed to this. A lot of the material you've seen in here belongs to them. They kindly allowed me to present it today. I want to thank them again. And I am not making any money on that book. Yeah, this is something in life. I don't know how to make money. But definitely go and check this book out. It's going to stay for a long while. It's the first review on the subject, and it collects a number of very fascinating works. Thank you very much.
Yeah, I think we have time for a few questions for Nathalie. Questions? Here.
I was interested in the fact that the slope of the distribution curves was different on Mars and on the Earth. And I wondered if gravity and its relationship to the density of the flow media might be something to look at.
We could look into that. I think that there has been work showing that somehow gravity and slopes sort of work around each other on Mars and the Earth, so they compensate somehow. But it's definitely worth looking at it. The thing I was thinking about, and there too I need to check, is that Mars is about 60% the size of the Earth. And maybe there are that many depressions that you can fit in that space compared to the Earth. And remember that lakes are lakes only because they are located and pond in the depression. So what we are seeing, in fact, is the size frequency distribution of the depression those lakes are sitting on, right? And so I was more thinking in terms of how many of those depressions can you fit in into the Martian, surface area. But yeah, it's just a completely new avenue. It was a new avenue 4 years ago on Earth. There is still a lot of work going on. What I like about it is that there is no fussing around mineralogy or around climate models and having to pull this and that. You look at the numbers, you plot them, that works, that doesn't work. If it works, you have a big problem because now you need to explain how that happened. And I think I know I've happened.
Other questions? Okay, well,
There's one here.
oh, here was one. Thank you, Don.
Real quickly, I want to thank you so much for your presentation. This must be a fascinating time to be a planetary, well, I was a planetary scientist. And my quick question was very speculative. What about thermophiles and things like that in a way out area like we see on Earth in the diversity of life?
What do you think
It's
that
a
a climbing
speculative question.
volcano
Is
at
that
20,000 feet? Do you really? I'm breaking my back with heavy backpacks and diving gear to just go explore those lakes if I didn't think that there was something that would look like what we could find on Mars. Here's my very optimistic view of things. If life ever appeared on Mars. And that's a big if. And as far as I'm concerned, I think, considering the resemblance between the two planetary environments between the Earth and Mars, not only I think that they would have all these diverse environment to really thrive, make the best of there, but I also do think they are still there because I see how resilient those species that we have been studying year after year in the Andes. You see the cladogram getting, more packed every day, every year. Well, every day, we're not there every day. But every year you see the chemistry of the water changing. You see those cladogram changing, but they are still here. Now I need someone, please, to go in those places and work at the interface between the water and the subsurface because I want to know how they are getting into there. And if you want my word on this, if they were there once, they are still here today.
Great, thank you.
Thank you, Nathalie. So as a small token of thank you for your talk, I actually have a wine glass engraved with the Drake equation and our logo, and you certainly
so you're getting
enlightened
the
us
before
on
you drink.
exactly. You certainly enlightened us on N sub E and F sub L today, and we very much appreciate that. So thank you.
Very much.